Okay, yeah. So first of all, I'd like to thank the organizers for this conference and giving me the opportunity to present my work. So today I'm going to talk to you about inflationary models in string theory. And one disclaimer in the beginning is that this talk has nothing to do about gravitational wave. So don't just decouple right now. There might be something novelty, that the novelty might lie somewhere else and it might be useful for you. Okay, so I'll be talking about inflationary models and I'm going to present two inflationary models. And I'm going to embed such scenario, that is the early period of accelerated expansion, in a string theory framework. So this talk will be on string phenomenology, and one subset of that is string cosmology, as Professor Zavala has already introduced to you what that is. So to give you in a simple words, what I'm going to do is that I will do model building. So we know that the inflationary models that we have seen or people usually study is a potential driven inflationary model, which means potential energy is the most dominated energy contribution. It is the most dominated one in terms of energy. And I will derive that potential from string theory, and it will have a physical origin, and the inflaton that is going to drive my accelerated expansion will also have a physical origin. So just to give you a hint of it, so the overall volume, so string theory, which has 6 extra spatial dimension, so the volume of that geometry in that 6 extra spatial dimension will act as my inflaton, or the scalar field driving inflation. So this talk will be based on these two papers which came out last year and is done in collaboration with Swagata and Pramod Shukla from JC Bose, Kolkata, and George Leonteris from University of Ioannina, Greece. Okay, let's move on. So in my talk, the 3 main keywords of my talk is, as usual, inflation, obviously, and string theory model building, how I'm deriving the potential and how my scalar fields are behaving, and moduli stabilization. I will tell you what all of them are. So inflation, as I don't have to introduce to you, but let me just, for the sake of brevity, let me just say. So inflation is a period of very early period of accelerated expansion, where in this very brief period of time, the universe has expanded by 10 to the power 25 order in all directions. And so in string theory model building, what I'm going to do is I'm going to choose my internal space. So in string theory, again, I have 4 spatial time and space. So 1 time and 3 space. On top of it, I have 6 extra spatial dimensions, because I'm talking about superstring theory. So in that extra 6 spatial dimension, I will specify my geometry. So for instance, I'll be considering K3 fibered Calabi-Yau. So which has like 2 complex dimension in this K3 fibration, and I will have 1 complex dimension and 1 real dimension in this base. So I have like a disk, and on each point on the disk I have this K3 fiber. And since I will be talking about 2 inflationary models, so one is volume inflation, the other one is fiber inflation. In one case, the whole volume of this 6 spatial dimension is going to inflate, and in other case, only this fiber is going to inflate. That is, it will stretch and squeeze in space-time and will give us inflation. Now, okay, so that is the topology. I mean, that's called the extra dimensional topology, like how am I specifying the geometry. And once I have specified the geometry, I can derive the potential, my aim. What is my aim? Okay. Now, why do we need inflation? To start with, I have to show you this plot, which is cosmological microwave background. And if you have attended Professor Subhadeep Mukherjee's talk, then you might already know that there was a time of decoupling where the photon started to roam freely. So it was originally it was trapped inside the atoms, and since the time of decoupling, these photons from this very early universe has started to come to us in all directions. And if you plot, and we have this 2D map of this cosmological microwave background, and if we don't have inflation and we try to, before that, so now in that CMB sky, if you take 2 antipodal points and if you check their temperature, then you will see that their temperature is mostly homogeneous and isotropic, modulo 1 anisotropy, which is 10 to the minus 5. So if you take 2 antipodal points, they are almost sharing the same energy as same temperature. And we know from thermodynamics that in order for two particles which are that much far away to have the same temperature, they must be in causal contact at some point in the universe. And if we check at the time of decoupling, they were not in causal contact. And what inflation does is it stretches that light cone towards an apparent Big Bang and towards negative infinity in conformal time, so that their forward light cone and the backward light cone, they match, and we can have an explanation for their same temperature. So their light cone match and they have sufficient amount of time to interact with each other. So that is the motivation to study inflation. Now, what is the, like, to do a theoretical model building, we can take one scalar field, canonical scalar field, say, minimally coupled to gravity. And if we given a potential of this form, the scalar field can also, the scalar field can roll down in this flat plateau. And when it is rolling down the flat plateau, the potential energy is greater than its kinetic energy because it's rolling very slowly, hence the name slow roll inflation. So when it is rolling slowly, the inflation takes place, and as it rolls down fast in this region, because it's a steep slope, inflation ends. And reheating, and I'm not going to be talking about reheating in my talk. Okay, so now you have already seen a lot of times, also in Dr. Swaga's talk, and also today, Gian Massimo was flashing all this. So it's all coming in the theoretical model building of inflation. So usually for single field models, you solve this the equation of motion, Klein-Gordon equation of motion, and you check how much inflation you need. So you have a potential, you have a scalar field. Now, in order to check how long it should roll and where exactly it should stop, you check all these epsilon parameters. You can write down also Hubble epsilon parameter and potential slow roll parameter, sorry. And there are model prediction also. You can also check, you can check those, the model prediction of your inflationary model through data as well, which is the Planck data, that is I'm showing here. So the amplitude of the power spectrum, the scale, the slightly scale invariance of the power spectrum, which is in NS, which is given by the 0.96. Then the amplitude of the primordial gravitational wave that is there in the universe. All of them are, it's not observed yet. So there is a bound on it. And the number of e-folds, which is a very important quantity, it tells you how much accelerated expansion you need, the minimum amount of that to solve the horizon problem that I was, well, by the way, so the previous one was horizon problem. The way I can give an explanation for the same temperature. Okay, so now the minimum amount is 60. Now you might see there is a star everywhere here. So this star denotes the pivot scale in the Planck data. So this minimum 50 or 60 e-folds is the amount of e-fold I need from the pivot mode crossing of the Hubble horizon and the end of inflation. The total amount of inflation could be more than that. There is no bound a priori on that. Okay, so now before moving on, so here we are seeing the Planck data and the model prediction of various toy models such as chaotic potential, 5 to the power 4 potential, natural inflation, like Dr. Ramkrishnan was showing. So these all models are toy models. So there are no physical origin for all these chaotic or quartic or alpha attractor, for instance. There is no physical origin. Alpha attractor can come from supergravity. But for the sake of my talk, if you can take natural inflation, and there is no origin a priori. Okay, so now in string cosmology, one can give an explanation for those scalar field as well as the potential energy. And not only that, so we know that in particle physics, in the standard model of particle physics, gravity is static and it unifies the three other forces of nature. But when we study cosmology in this high energy scale, what happens is we know gravity is dynamic. So it's an expansion of space-time. And also in this calculation, we have already seen from Professor Gian Massimo's talk that it incorporates quantum mechanics. So we might need a theory which can incorporate both the quantum mechanics and the gravitational general theory of relativity, and we can have an effective field theory of incorporating all of that. So string theory for last 4 decades being one of the leading candidates, but not only just one. There are many other quantum gravity candidates probably. So string theory being the leading candidate can provide those potential energy, and once you because string theory I'll be considering 10 dimensions, and once you dimensionally reduce, which means once I get rid of this extra dimension, you get a 4-dimensional effective field theory. And in that 4-dimensional effective field theory, you can get not only just one, you can get many scalar fields, which are known as these moduli, which are massless scalars stemming from this extra dimension, and they can act as this inflaton or for quintessence scalar in your 4-dimensional effective field theory. They are massless with gravitational strength interaction. And the way your geometry in the 60 is its design will be manifested in this scalar fields, which is this moduli. And one, just like I said, we just don't get one, you get many, and it also comes with another problem. So, I mean, since you get many, you don't have to just study one single field inflation. You can study multi-field inflation, like Professor Sonia Pavan was showing yesterday. She was studying 3-field inflation to start with. And not only that, so once you get this many massless scalar fields in your effective field theory, what happens is there might be problems with fifth forces. Because we know, I mean, it's strongly bounded from the tabletop experiments, there is no fifth force. So to avoid that, one has to do moduli stabilization. So what do I mean by that? I will create for all these moduli, I mean, that is the hope, that for all these scalar fields that I get from dimensional reduction, I will generate a potential for all of them, so that in this potential, in the minima, the fields are trapped, and they have hopefully they have a positive mass in all the minima. So if I have already motivated you, let us go forward. So string compactification, again, I mean that I have started with 10 dimension. So this is our 4 dimension, 1 time and 3 space. And on top of that, I have 6 extra spatial dimensions. So this total, which is a chiral theory, this is 10 dimension, our 10-dimensional superstring theory. And you can also go beyond, you can add more spatial dimension, and that will be your bosonic string theory, which we don't usually study because it lacks the fermion. So I'll be considering this 10-dimensional superstring theory, and there is an energy scale that we have to consider. So you have this MPL, which is the physically possible, the highest mass scale. Between MPL and MS is the mass of this tiny vibrating string, which is the building block of string theory. So between this MPL and MS, there lies the higher dimension, high energy counterpart of string theory, and upon quantization of in this energy scale, you get these 6 types of string theory, and I will be considering type 2b for phenomenological purposes. Below this, which is the low energy string theory, and this low energy 10-dimensional, which is also called 10-dimensional effective field theory, and the mass spectrum of this string theory is the same as 10-dimensional supergravity. And once I dimensionally reduce, I get this MKK, that is a Kaluza-Klein reduction. So I go down to our 4-dimensional effective field theory, and this is where I would like to study my inflation. So I will derive my scalar potential, and my fields will come down here and sit in the Lagrangian that I will be writing in 4-dimensional, right? Okay. So now I will be considering Calabi-Yau threefold because it reduces the number of supersymmetry. So supersymmetry is required because it eases up our life, and for the sake of calculation as well, I need at least n equal to 1 supersymmetry. But I will show you as I go on, since I will have a de Sitter minima, that even 1 supersymmetry will be broken. So we are fine. For the inflationary potential that we'll have, will not have any supersymmetry. Now, why am I saying all that? Because we will usually, for phenomenological purposes, we choose this Calabi-Yau threefolds, and we don't know a priori the exact metric of this Calabi-Yau threefold. But what we know is the submanifolds of this Calabi-Yau threefold. So we can count how many submanifolds that is in cycles, like 2 cycle, 3 cycle, how many of them are there. And those numbers will tell us what is the number of my scalar fields that is there in my 4-dimensional effective field theory. Okay, so one of them is scalar moduli, which is particularly important because they will play the role of my inflaton scalar, which is related to the overall volume of the internal space. Then there structure moduli, which tells you what is the shape of the internal space, and there is also an universal scalar, which is axiodilaton, which tells you what is the strength of interaction of each string. So it is telling you the string coupling. Okay, so as I said, so in my talk, I will consider these two to be stabilized by some mechanism, and already, okay, these two are stabilized by some mechanism, and I will only inflate with scalar moduli. Okay, so now for the rest of the talk, I will address moduli stabilization, but I might have to speed up. I will try to find the de Sitter vacuum, and if found, I would like to study what is their inflationary implications. Okay, so now this is a busy slide, but the takeaway from this slide is the following. After dimensional reduction, you are already in the 4th dimension, and in the 4th dimension, you can actually write down a potential for all these scalar fields, that is the complex structure and scalar moduli, through this well-known superpotential and scalar potential that was first given by Gukov, Hafa, Witten, and this scalar potential. And due to the form of the scalar potential, once you write your full scalar potential for all these scalar field that you get from higher dimension, that is a complex structure, scalar moduli, and axiodilaton, due to the block diagonal form of the scalar potential, the dependence of scalar moduli drops out. So one of the moduli, which I am mainly interested in. So the way forward is the following. So as you can see, if you just, the slides will be available, you can just simply plug in, and you can see there's this VFT, which is the scalar moduli, it's equal to 0. So what you have to do is you have to go beyond the tree level. So there are two strings interacting with each other, so you have to go, you calculate your perturbations, right? You have to go beyond the tree level. So you have to actually consider the perturbative corrections and non-perturbative effects as well, if needed. So in my talk, I will show you, because there are various, already there are various models available for string inflation, right? Now, I'll try to motivate why our model stands out in terms of adding these quantum corrections. So the idea is the following. I will have a potential generated for these scalar moduli. They usually, from the construction, it has been shown many times that usually the minima you get is ADS. So you have to add something to uplift to de Sitter, and I'll be interested in a three-field inflation. So I will lift, I will have one flat direction, and I will displace that scalar field along one of this flat direction, and I will let it roll down, and which will incur our required amount of inflation. Now, these are the type of corrections that is possible to make your VFT, that is the potential for the scalar moduli, non-zero. So I will be adding these 4 corrections. So if you have questions, I will answer in the end, but let me just flash these corrections and go to my results. How long do I have? 7 minutes? Okay. So now you might all know that what is large volume scenario. Large volume scenario and KKLT. These are the two well-known construction which have first shown how to, and GKP as well, how to first stabilize all these moduli, and you can have de Sitter model building in string theory. So LVS being one of the most studied, because it has large volume, it has large volume. So the volume of this internal space is large. And why is this needed? Because in order to have your 4-dimensional effective field theory under control, you always, you can apply semi-classical approximation. So you always need to, you always try to be in either in the large volume, both large volume scenario and weak coupling limit. So large volume scenario was able to do so, because you can see, if we just ignore, this is scalar potential and superpotential, and in large volume scenario, there is an interplay between perturbative correction and non-perturbative corrections, and the final volume, the wave of the vacuum expectation value of the volume has this exponential factor there, and due to the appearance of this exponential factor, you get large volume. Now, we will do something similar, but the novelty of this model is that we don't add any non-perturbative effects, because perturbative effects in string theory are well known. You can do your top-down approach, and there is a counterpart of all these perturbative corrections. There is a counterpart in 10D, but it's debatable. But There is no counterpart of this non-perturbative effects in 10D. So it is always good to not add these corrections. And also I will show you, if I get time, that in fiber inflationary model, due to the non-appearance of these perturbative effects, we have no bound on the field excursion, because how long the inflation should last, it's important for that, and also for light bound and so on. Now I'm going to do the same thing, but only with perturbative corrections. So you can see I'm only adding terms in the scalar potential, and I can again have this large volume scenario due to 1 over GS square, because GS is always small, and you can see like just plugging in these two numbers, you can get this large volume scenario, and the minimum is again positive, negative. Okay, so so in this now, the model that I have, or the internal space that I have, it has 3 scalar fields. Now I can check what is their masses, because I am interested in inflationary model. I can always check their masses, and I can get rid of, I can integrate out the heavier one, and I can work with the less massive one, right? And I have done the same thing. I have changed basis for the sake of simplifying the potential. And here I'm just showing you that how to get rid of these 2 fields, and I can write down a simplified form of the scalar potentials. Like you can see that one of this is actually less massive compared to the other two. And this is the simplified potential, where you can see phi is my scalar field, which in this case is related to the overall volume of the internal space. It's a 6D volume, dimensionless. And this potential has an inflection point as well as nice plateau, which might be interesting to study this primordial gravitational wave. One has to check, but that's future work. And so these are, let me just quickly go through. So here I have added, not here. So here I have added more corrections. Like in all of them are perturbative order. So I have added the standard alpha prime cube correction. I have added the higher derivative f to the power 4 corrections. And to uplift, I have added d terms also. So adding all that, which is like, you can see exponential, but they are not non-perturbative corrections, they are just volume. So exponential minus phi is just 1 over volume. Okay, and if we check the model prediction, it has a nice minima and the maxima. Maxima is not needed, but minima is needed for enough efforts of inflation and reheating. And so we have, after plugging in some parameters, this is just one benchmark model, but there are, in the paper you can see there are many. So you have, we have large volume as well as the model prediction is under control. I can come back to it after 2 minutes. Okay. Okay, and so this is the first part where our scalar field was the overall 6-dimensional volume. Now for the fiber inflation, our inflatant scalar will be 4-dimensional volume. So the fiber of this K3 fiber Calabi-Yau will act as the inflatant. And again, we have this potential where only perturbative effects were considered. And one important thing about this model is that this K3 fiber Calabi-Yau has the same symmetry as the toric orientifold. So that's why I can write down this overall volume, because the K3 fiber Calabi-Yau has many other forms of volume, which also sometimes incorporates this blow up modulus, like this small cycles. But here we can write down it as we can consider it as a torus, like 4-dimensional 3 torus. Okay, and again, if we check the model prediction, it is within the Planck bound, and the potential has a shallow de Sitter. It is a shallow de Sitter potential, and so the model prediction is the volume is large, and GS, the string coupling is small, and all these parameters are within the Planck bound. And one thing that I wanted you to see is that in the maybe I will tell it in the conclusion. 1 minute. Okay, good. Okay, so to conclude, I have shown you the global embedding of the non-perturbative LVS, and why perturbative LVS is required, because there is non-perturbative effects are not well understood from 10-dimensional point of view. So perturbative LVS is always preferred, and I have shown that this perturbative LVS type inflation is robust against addition of even further corrections in perturbative level. So if you add this higher derivative corrections as well as these d-term effects, the total, the potential still can hold inflation. There could be sufficient amount of inflation. The volume inflation that I have shown you is a small field inflation, and we know there are swampland conjectures. So if you, this volume inflation is actually is in compliance with the distance conjecture, because it is a small field inflation. And in fiber inflation, there is something nice that happens, is that since there is no non-perturbative effects and we don't need any exceptional del piezo divisor, it's just a it's like a 4 cycle. So since you don't have that, there is no bound exposed on the field excursion, which is always good, because the previous fiber inflationary models had that problem, and it is a well-known problem which is absent in our case. So yeah, so with that I would like to end my talk. Thank you.
Okay, so questions? Yeah, go on.
What is the string scale in this scenario?
String scale,
yeah.
LS. So LS is usually, with the, LS is related to the Planck's. So LS, and we haven't checked it explicitly, but what we have checked is that whether we, I can tell you our number directly, but we, we have checked the hierarchy. So MKK should be, MKK should sit on the, should be the highest scale. MKK, then the moduli mass, and the string scale should even sit in the, before that. So the hierarchy of MS, MKK, and the moduli mass, that is there. But exactly the number, I don't think I have checked it explicitly.
Yeah, the reason I'm asking is I want to know how large a hierarchy between Planck scale and string scale you have. And it may have some implication.
So we are in the large volume scenario.
Yeah.
So in large volume scenario, I think, if since the volume is large, and because string scale and Planck scale, they are related by GS over square root to the square root of volume, right? Okay. And GS is small, one can calculate. So GS is 0.3. And the square root V, and since V is 15,000 in the last part, okay. So it's 0.3 by square root 15,000. So yeah, yeah. So that is the number, how much it will be, 10 to the power 4 square, 10 to the minus 3, 10 to the minus 3. So M Planck is 10 to the minus 3 times MS. Okay. Sorry, the other way around. MS is 10 to the minus 3 times M Planck.
Yeah, then can you give some comment about the action in this scenario?
Action, yeah, so the actions, obviously the actions are all there. So they are all the saction of the model. Yeah. So these all 3 scalar moduli that I'm showing you, although we call it phi, but they are not action, they are the sactions. And we consider for this case, this action are sitting at their minima, because they're usually the massless counterpart, right? So they are at their minima, which is usually at 0. So they are at their minima. But I think you are you are worried about this dark radiation, or
no, in regard of this case, associated with the action. Typically, the string action is around similar to the string scale. So in this case, you have this symmetry breaking scale associated with the action to be similar to around the intermediate scale. Is it the case?
Sorry, can you ask your question again? The action scale and the symmetry breaking scale.
In the string theory, usually people worry about this string action problem. In case you want to use the string theory action to be the QCD action, because the string theory action to have a symmetry breaking scale quite larger than the intermediate scale. But in larger volume scenario, as far as I understand from the literature, it can be lower than the intermediate scale. Is it the same in your scenario? That is my question.
We have first of all, we did not check about the mass scale of the actions a priori, but the volume in, so we have studied 2 models. In one case, the volume is smallish, so that might cause some problem, you're right. But in the other case, the volume is sufficiently large, if I understood your question correctly. Yeah. So maybe that one is fine. The fiber inflation one, maybe it's fine. Yeah. Yes.
It's working. Yeah, it's related precisely to the actions. Aren't they flat directions?
So to start with, so we have our Kähler potential, we have our superpotential, then we plug in all these effects. Yeah. So we plug in all these effects, and you can see like there is this V, which is directly related to the section part. So we are
there
not.
There are no actions. Yeah.
There are no actions. So we
it's
consider
flat.
Yeah. I mean, yeah. So usually, I mean, they are minimized and 0. I mean, it's usually like at phi equal to, I mean, theta equal to 0 is that is the minimum of the action. So we put them to 0. Yes. I don't know if it will be a flat direction because. Yeah.
So yeah, because there's no
potential generated for the action.
Exactly.
So in that sense, yeah, you can call it flat direction. Yes.
So they have to be stabilized at some point. Right?
Yes. Yes.
Then you reintroduce non-perturbative terms.
I reintroduce.
Non-perturbative terms will lift this flat
non-perturbative terms. Yeah. Okay. Yeah, but so this model that we have considered, I'm not sure about that, but because this geometry that we have is a K3 fiber Calabi-Yau, but has the same symmetry as a toric orientifold, where we cannot add any, I mean, because of the structure, we cannot add any non-perturbative effects. So, because I mean, to stabilize all these actions, you need this instant and corrections and poly-instant and corrections, right? So the geometry is such that we can't add all that. So I don't know. Yeah, maybe I'll check. Yeah. Thank you.